Hey everyone, welcome back to Chem Story. Today, we're going to look at how alcohols can be synthesized. We'll walk through a few different methods, one step at a time, and see how we can start with completely different molecules, but still end up with the same functional group, the alcohol. By the end of this lesson, you'll have a solid overview of the key strategies chemists use to make alcohols in the lab. All right, let's get started. Let's start with one of the classic ways to make an alcohol, converting an alkyl halide into an alcohol. And one way to do that is with an SN2 reaction. Here's how it works. A hydroxide ion, acting as a nucleophile, attacks the carbon that's bonded to a halogen, like chlorine. As that happens, the leaving group, Cl- gets kicked out, and the OH group takes its place. Now because this is an SN2 reaction, it all happens in a single step. And because it's a backside attack, the stereochemistry gets flipped. Bottom line, if you're working with a primary alkyl halide, this is a super reliable way to make alcohols. Now let's look at another way to make alcohols, this time using an SN1 reaction. This method works best with tertiary alkyl halides, or sometimes secondary ones if the conditions are just right. Here's how it goes. First, the halide leaves on its own, forming a carbocation ion intermediate. That first step is pretty slow, and it's the rate-determining step of the whole reaction. Then, water steps in as the nucleophile and attacks the carbocation ion. After a quick proton transfer, you get your final product, an alcohol. One thing to keep an eye on is rearrangement. Carbocation ions love to shift around to become more stable, so you might not always get the product you were expecting. But overall, the SN1 pathway is a solid option when you're working with the right kind of alkyl halide. Now let's move on to another major route, making alcohols from alkenes. The first method we'll look at is acid-catalyzed hydration. It's a pretty straightforward reaction. You start with an alkene, and in the presence of water and an acid catalyst, like H+, the double bond reacts and gets converted into an alcohol. Here's how it works. The double bond grabs a proton and forms a carbocation ion intermediate. Then water attacks that carbocation ion, and after losing a proton, you're left with an alcohol. Just remember, this reaction follows Markovnikov's rule, so the OH group adds to the more substituted carbon. It's a quick and simple way to hydrate alkenes, but because there's a carbocation ion involved, rearrangements can happen, so that's something to watch out for. If you want to avoid rearrangements but still stick with Markovnikov addition, this next method is a great choice. It's called oxymercuration-demercuration. It's a two-step process. In the first step, the alkene reacts with mercuric acetate in water and THF. This forms a bridged intermediate, a mercurinium ion, and water attacks the more substituted carbon, just like in acid-catalyzed hydration. Then in the second step, you add sodium borohydride, which gets rid of the mercury group and gives you the final alcohol. What's great about this method is that there's no carbocation ion, so you don't have to worry about rearrangements. So overall, you still get the same Markovnikov selectivity, but with a lot more control over the product. Now let's look at a third method, and this one's a little different. It's called hydroboration oxidation. This reaction follows anti-Markovnikov addition, which means the OH group ends up on the less substituted carbon. In the first step, the alkene reacts with borane in THF. The boron and hydrogen add across the double bond at the same time in a syn addition. Then, in the second step, you treat it with hydrogen peroxide and base, which replaces the boron with an OH group. So what do you get? An alcohol on the less substituted carbon, and it keeps the syn stereochemistry. So overall, this method gives you the opposite regioselectivity from the previous two, which makes it super useful when you need more control over where the OH group ends up. Here's another way to make alcohols from alkenes, and this time you get two OH groups at once. It's called dihydroxylation, and it gives you a syn 1,2-diol, which means both hydroxyl groups add to the same side of the double bond. The reagent we use is osmium tetroxide, followed by a reducing agent, like aqueous sodium bisulfite. This reaction adds two OH groups across the double bond in one smooth, concerted step, and with syn stereochemistry. It's a super useful reaction when you want to build vicinal diols from simple alkenes. Next up, let's shift our focus to carbonyl compounds, like aldehydes and ketones. These can be converted into alcohols through reduction, And for that, we usually use a metal hydride reagent. Here's how it works. The hydride ion, H-, attacks the carbon in the carbonyl group, breaking the double bond and turning it into a single bond with an OH group. If you start with an aldehyde, you end up with a primary alcohol, and if you start with a ketone, you get a secondary alcohol. Common reagents for this are sodium borohydride and lithium aluminum hydride. This is one of the most reliable and widely used methods for making alcohols from carbonyls. Now let's take that a step further. We can also reduce carboxylic acid derivatives, like esters or acid chlorides, to make alcohols. This also uses a metal hydride, typically lithium aluminum hydride, but the reaction takes place in 2 steps, not just one. First, the acid derivative gets reduced to an aldehyde, and then that aldehyde is reduced again to give a primary alcohol. Since acid derivatives are more stable than aldehydes or ketones, this kind of reduction usually needs stronger conditions and excess hydride, but the basic idea is the same. You're breaking the carbonyl double bond and swapping it out for an OH group. So depending on what you start with, whether it's an aldehyde, a ketone, or an acid derivative, you can make different types of alcohols just by choosing the right reducing agent. Next, let's talk about Grignard reagents. They're a powerful tool for making carbon-carbon bonds and forming alcohols at the same time. When you add a Grignard reagent to a carbonyl compound, the nucleophilic carbon in the Grignard attacks the electrophilic carbon in the carbonyl group. If you start with an aldehyde, this gives you a secondary alcohol, and if it's a ketone, you get a tertiary alcohol. Once the Grignard adds in, you just do a standard aqueous workup, usually with a dilute acid, and you end up with your alcohol. This reaction is great because it doesn't just make OH groups, it also lets you extend the carbon chain, which makes it super versatile in organic synthesis. Grignard reagents can also be used with acid derivatives like esters or acid chlorides. Here's how it works. First, the Grignard reagent attacks the acid derivative, kicking out the leaving group and forming a ketone intermediate. Then, a second equivalent of Grignard comes in and attacks that ketone. After an acidic workup, you end up with a tertiary alcohol. Now let's look at one more strategy, making alcohols from epoxides. Epoxides are those strained, 3-membered rings, and because of that strain, they're very reactive. When you treat them with a nucleophile, like a Grignard reagent or an organolithium compound, the ring pops open and you end up with an alcohol on one side. The nucleophile usually attacks the less hindered carbon in the epoxide, and after an acidic workup, you get either a primary or secondary alcohol, depending on the structure. Even hydride donors like lithium aluminum hydride or sodium borohydride can do the same thing, adding hydrogen and opening the ring to form alcohols. So overall, epoxide ring opening is a great way to make alcohols, especially when you want to add new atoms while also forming an OH group. Finally, let's talk about a slightly different way to open epoxides, this time to make anti-1,2 diols. If you treat an epoxide with acidic conditions, like H3O+, the ring opens and adds OH groups to both carbons, but on opposite faces. That gives you anti-stereochemistry. And if you run the reaction under basic conditions, like with OH-, you still get anti-addition. The mechanism's a little different, but the end result is the same. So either way, you're converting an epoxide into a 1,2 diol, and you're getting that anti-geometry between the 2 OH groups. All right, that wraps up our full tour of alcohol synthesis. We've looked at all sorts of methods, from SN1 and SN2 to hydration, reductions, and even epoxides. Each pathway has its own conditions, selectivity, and advantages. So depending on what you start with and what kind of alcohol you want, you can pick the strategy that works best for your synthesis. Thanks for watching. And as always, I'll see you in the next Chem Story video.